Time?
Yes.
Okay, 1 o'clock. So let's first say about the midterm. Midterm next week on Wednesday. And just like before, if possible, please attend the 11 o'clock class on Wednesday to do the midterm. If not possible, of course, you can. So for the midterm, don't forget practice test, homework assignment, and make sure that you're able to do image formation by lenses and by mirrors. And the image formation with diverging lens may not be trivial. So train it, make sure that you know how to do it fast. It is easy once you figure it out. Okay, so again, image formation by lenses has to be trained for the midterm, especially for diverging lenses could be tricky. And converging lenses also, if you don't train it, you're going to wonder how to do it. Okay. Yeah.
So is it just going to cover 25 and 26? Or is it 25 as well?
So the test is on 24, 25, and 26. Okay. The last 3 chapters that we haven't done. So chapter 24 is electromagnetic waves, which is a slightly different point of view of this material, different from the point of view of geometric optics. The homework assignment, try to finish it early so that we to be able to finish with the preparation for the midterm and to start the new material. So next chapter, chapter 27 is interference in diffraction material that is familiar from sound waves. Yes.
Have you decided the midterm will be next Monday or Wednesday?
Wednesday.
Okay.
Wednesday, April 14th. No. What day? April 13th. Yeah, April 13th. Okay, so nobody looked at the homework assignment. No questions about homework? No? Okay, in that case, let me tell you about human vision. After that, I can write a few formulas on the board. But if some question comes up, just feel free to interrupt. So far, we have thin lens equation. One over pi. And linear magnification, simple equation, which says that it is di divided by do, but with negative algebraic sign. And again, the place where people make mistakes when those 2 equations are used is in the sign convention. So we said that the focal length is a positive number for a converging lens and the negative number for a diverging lens. Di is a positive number if the image is formed to the right. Image on the right. Right. Image on the right. And negative number if image is on the left of the lens. And finally, HI is a positive number if the image is upright, and it is a negative number if the image is inverted. So all the other distances are going to be with positive algebraic sign for the case of a single lens. If you have more than one lens, the situation may be different, because the image of the first lens may be used as an object of the second lens. But again, we don't have problems of that type in our textbook. Now, using the sign convention and using the two equations that are on the board, you can answer all questions in the homework assignment that deal with simple magnifying glass or objective of a camera or a projector, and you have examples like that. Now, what you have to emphasize on this chapter, well, everything is important because everything is connected, but since you're biomedical majors mostly, you have to get ready to encounter multiple questions related with the human vision. And in order to answer those questions, this is what you need to know. If you have the human eye, maybe something like this, roughly speaking, and here's the principal axis. So the human eye consists of multiple layers, transparent materials with different indices of refraction, but the effective focal length of all those multiple layers is as if you have a converging lens. Now, that converging lens has variable focal length because the lens inside the human eye can change its thickness by contracting or relaxing muscles in the eye. So as a result of that, an object that is located somewhere in front of the eye, an image of that object has to be created exactly on the retina, and the retina is located on the back of the eye. Ideally, that image, so the muscles of the eye change the focal length of the lens of the eye in such a way that the image to be created on the retina, and preferably at the place of the retina with the highest density of photosensitive cells. Well, of course, there are limitations. So you cannot, the human eye cannot detect objects, cannot see clearly objects that are very close to the eye, just because the focal length, the effective focal length of the eye cannot be made infinitely small. So the closest distance at which you can see clearly an object is called near point of the eye. And the for a normal vision, the near point is at 25 centimeters, approximately 25 centimeters from the eye. So people that have very good vision may have near point that is closer than 25 centimeters. And as people age, the near point moves farther from the eye. In other words, the near point distance increases as we age. Similarly, the most distant object that you can see clearly is at a distance called far point. For normal vision, the far point is at infinity. So far point is at infinity. So let's make it this distance from here to here should be at infinity. Now, if the near point is not at 25 centimeters, but let's say it is at a distance, let's say 30 centimeters, this means that you cannot see very well objects that are close to the eye. And this is what we call farsightedness or hyperopia. And you correct this vision problem with a converging lens of eyeglasses or contact lenses. The philosophy behind correcting the vision is simple. The lens of the eyeglasses, let's say, the lens has to take the object and form an image of that object at a place, at the closest place where the eye can take it over and see it. And that closest place is the near point, whatever is the near point of that person. Yeah.
What is the number for fair point?
The far point, the normal vision for the far point is at infinity. Far point is at infinity. Infinitely distant objects are visible by a normal human vision. And this is why you are able to see, for example, the moon clearly, right? Or the distant stars or galaxies. They're very far away, almost at infinity, and the normal vision is able to form a clear image of those infinitely distant objects. Okay, so it will be desirable to have an example of this correction of farsightedness and also nearsightedness in a state in which the far point is not at infinity, but it is somewhere closer than infinity, let's say at 10 meters. This means that you see clearly objects that are close, but not very clearly objects that are distant. And this is corrected with a diverging lens of eyeglasses or contact lenses, as we're going to see in a minute. Also, when we're talking about lenses of eyeglasses or contact lenses, instead of focal length, we use diffracting power, defined as the inverse of the focal length if the focal length is given in meters. So this is what we call refracting power, or well, refracting power. And it is measured in inverse meters, which we also call diopters. Now, keep in mind that for converging lens, the focal length is a positive number. Therefore, the refracting power is going to be a positive number. While for diverging lens, the focal length is a negative number, and therefore you need the negative algebraic sign. You have negative refracting power for diverging lenses. Okay, so now let's do an example now, which eyeglasses. And as an example, I can use something from my notes. But it is better to use a homework problem because we can project it on the board, and people that are online can see that problem on website. So as an example, look at homework problem number 10. Homework problem number 10. They are talking about far-sighted person. Far-sighted meaning hyperopic eye, which means that you see very well on the distance, but not that well close. And this is corrected with a converging lens. In other words, lens with positive focal length, positive refracting power. And they say this, they say that the near point of that person is at 48 centimeters. Remember, the normal near point is at 25. She wears eyeglasses that are designed to enable her to read a newspaper at a distance 23 centimeters. So this means that objects that are placed at 23 centimeters from her eye, the lens of the eyeglasses take that object and creates an image at the near point. And once that image is at the near point, the eye can take it over and examine it. So they say that she wears eyeglasses at 2 centimeters from the eye, and you have to figure out the focal length that those eyeglasses need to have. And always when you have a problem with eyeglasses or contact lenses, always draw a diagram. Without this diagram, it is very easy to be confused. And here's the diagram. So here is the lens of the eyeglasses. Here is her eye. Here. They say that the distance between the eye and the eyeglasses is 2 centimeters. And they say that you need the principal axis, of course, like always. They say that you place an object at 23 centimeters from the eyes. So maybe place the object right here. This distance is 23 centimeters. And the idea is that the lens of the eyeglasses take that object and create its image at the near point. They say that the near point is here, at a distance 48 centimeters. Okay, so this is what is given. And now you have to infer the distances DO and DI from this diagram. So DO is distance between the lens of the eyeglasses and the object, and that distance is right here. So looking at the diagram, you say that DO is equal to 23 minus 2 is 21. So I figured out that distance from the diagram that I drew, not from somewhere else. In a similar manner, the idea now was that the image of that object is created at the near point. Therefore, the image is somewhere here. And therefore, the distance DI becomes, well, it is this distance, 48, minus 2 is 46. But since this image is created to the left of the lens, left says image has to be negative number. So you have to insert the minus sign. Again, the trick was to figure out DI and DO, and the way to figure it out is just by looking at the diagram and following also the sign convention. So in part A of this problem, so this is problem number 10, we said, in part A of this problem, they're asking us to figure out the focal length of the eyeglasses. And you say, well, you say that the focal length comes from the chin lens equation, DI plus 1 over DO. So you have to do the arithmetic here, but from this equation, so DI we said is negative, and DO is 21, so it is 1 over 21. And when you do the arithmetic, so you have to subtract those two fractions using your calculator, and the focal length is going to be the inverse of that number. So the focal length is going to be 1 over 46 with negative sign plus 1 over 21 with positive sign, but all of this inverted. And when you do the arithmetic, you have to get 38.6 centimeters. In a similar manner, you handle part B when the distance between the lens of the eyeglasses and the eye is 3 centimeters. So again, when you hear eyeglasses or contact lenses, this diagram is going to be needed to make sense of the distances. And on the midterm, you're going to have probably more than one problem of this type. And for those problems, you have to show the diagram, and the diagram is going to be worth some points. Any remarks and questions? Okay. Are you up to some wake up conceptual questions maybe on the screen, or you want me to talk more about geometric optics before we do? Yes.
I'd like some conceptual questions, but sorry, on part B, how did you get the 36 after part A?
Oh, I didn't get it. I didn't do part B. But part B is the same like part A. You just change those 2 centimeters into 3 centimeters, which is going to change DO. DO is going to become 20. DI is going to become negative 45, and you do the same arithmetic. And you're going to get the answer. But again, any more remarks, questions? So I see that not that many people wear eyeglasses here in this classroom. So should we give the difficult problems to people with no eyeglasses? What do you say?
I mean, obviously they see better, so.
Yeah, people with eyeglasses see better clearly, so they're going to. Well, let's see how many people are going to wear eyeglasses when the time for the test comes. We're going to decide who is going to get the difficult problems and who is going to get the easy problems. Okay, now, so since you're not asking any questions about homework problems, let me finish this chapter and then we can talk about some conceptual questions to the board. So in the textbook, they give you a formula for magnification by a simple microscope. That formula is not derived, but you can use it. That formula involves the focal length of the objective, the focal length of the eyepiece, and the distance between them. So knowing those 3 numbers, you can calculate the magnification of simple microscope. The same thing about the magnification of a telescope, refractive telescope, simple. Now, those formulas are given not in terms of linear magnification, M, but in terms of angular magnification, capital N. So let's figure out what this angular magnification actually means. So the angular magnification of any optical instrument, capital M, is defined as angle at which you see the image provided by the optical instrument divided by the angle under which you see that same object without optical instrument. And look, let's start with the angle theta, the angular size of an object that you see with naked eye. So here is an object, and let's say that, well, maybe the distance between the object and your eye is larger than the size of your eye. So let's say that this is your eye, maybe. Or you can always say that here is the angular size, theta, of your object. So here, the size of the object, of course, from here to here is HO. And, well, distance, you can call that distance between the object and the eye, DO. And this is what you have. Now look, our definition for angle in radians is the ratio of, so angle in radians, here is one angle. Here is the angle theta, and here is the arc enclosed by, defined by this angle. And here is this distance is the radius of this circle to which the angle has this circular arc. So theta in radians is defined as the length of this arc. So the length of this arc, call it arc, the length of that arc, divided by the radius r of this circle that you invented. This is our definition for radians. And following that definition, the angle under which you see this distant object would be, well, it should be the length of this arc right here, from here to here. But the length of that arc is approximately HO. So your angle theta is approximately HO divided by the radius, which is DO. Approximate, but pretty accurate approximation. Now let's express let's find the angle of magnification of a simple magnifying glass. So if you remember, a simple magnifying glass is a system in which you place the object between the lens and the focal point. This is where you place the object. Now, so for a magnifying glass, the image is going to be formed somewhere here. And that image is probably going to look like this. And therefore, the angle under which you see that image, this is the angle theta prime. Well, the eye may be somewhere here. But again, the angular size of your image is theta prime. And let's figure out the value of this theta prime. Clearly, this is HI. And to a good approximation, this distance, well, this I exaggerated, but in general, this distance here is DI, approximately. Because the real DI is only here. The real DI is only here. In other words, the angle under which you see the image theta prime, that angle theta prime, is approximately equal to HI divided by DI. Now, I want to get rid of HI and DI. Those are intermediate images formed by the lens itself, not by my eye. And to do that, I'm going to use the formula for linear magnification. So the formula for linear magnification says HI divided by HO is equal to negative di divided by do. This means that hi divided by di is equal to negative ho divided by do. And I substituted here, but I substitute hi divided by di with its equal, negative ho divided by do. And I should take the absolute value of this. Because distances cannot be negative, when I'm calculating the angle, it doesn't make sense to put negative lengths, because this is the definition for angle. Well, so this is theta prime becomes equal to ho divided by do. In other words, we lost the minus sign. And now take those two results. Actually, you can modify a little bit more the result for the angular size of the object by saying that, well, your clearest vision is going to happen when the object is at the near point. This is going to be your biggest angle that you're going to see the object. So this is going to be ho divided by the near point distance, call it n. So taking those two results, you get for theta prime, you get ho divided by do, and for theta, you get ho divided by the near point. You see that ho cancels out, and you get that angular magnification of a simple magnifying glass becomes equal to the near point divided by do. This is what it comes out to be. So this is one quite accurate result. You can use that result in alternative forms. For example, using the thin lens equation, you can write this result if you want as 1 over do, right? 1 over do, but this is n times 1 over f minus 1 over di. If you want. So you can use this or this, or you can even simplify it further by saying that you're going to see best your image if that image is formed at the near point. So if you say that di is at the near point, but remember that di is in front to the left of the lens, so you have to insert a negative sign to make it, to take into account that. If you do this, you're going to get n times 1 over f minus 1 over minus n. So we're doing this for the best angular magnification. And in this best angular magnification, when you plug in the numbers, you're going to get that this angular magnification for the best case is equal to n divided by f plus 1. So this is the best angular magnification a lens with focal length f can provide to a person with near point n. So using similar way of reasoning, you can prove that the angular magnification of a simple microscope, and I'm not going to give any questions that use those formulas, but they are given in the textbook, and you often use microscopes, I guess, in other classes. So the angular magnification of a simple microscope can be shown using similar techniques to be L minus the focal length of the eyepiece times the near point of the person divided by the product of the focal length of the objective and the focal length of the eyepiece. Here, L is the distance between the objective and the eyepiece. And for a telescope, so in other words, for a large angular magnification of a microscope, you want to minimize this product. You want the product of focal length of objective tank and the focal length of eyepiece to be the smallest possible number. While for a simple telescope, you can show for a simple telescope, it is even a simpler expression. The angular magnification of a simple telescope is negative the focal length of the objective divided by the focal length of the eyepiece, which means that you want objective with long focal length and small focal length of the eyepiece. The minus sign of this formula for a simple refractor telescope, the minus sign indicates that the image is inverted, upside down. If you want to have images that are up rather than inverted, you have to use additional lens or lenses added to either the eyepiece or beyond the eyepiece to have a terrestrial type of telescope. So knowing all of this, let's see questions and remarks. If no questions, let's look at the following conceptual questions. So this is tricky, and this is why I have chosen it. So look, large index of refraction means slow light in that material. if you enter large index of refraction, you're going to be refracted closer to the normal. The slower the second medium, closer to the normal you're going to get. And here you get closer to the normal in this situation. So this is the slower medium than this one, right? And therefore, where is the light faster? In one. Okay, get ready for the next question.
So the medium with the larger refraction of light is going to be the slower medium, right?
That's correct.
So it, based off of the diagram, it would look like the slowest medium would probably be 2, because it's the closest to the normal, right?
Yep.
So that would, N of 2 would be first,
Yes.
and then that's as far as I've got.
Well, this narrows, well, you have only one situation in which N2 is largest. Right?
So how can you tell that
So look,
one or
if 1 and 3 were equal indices of refraction, this would go parallel to this dash light. But it goes to a larger number. Therefore, 3 has smaller index of refraction than 1. 1 is larger. So it should be 2, 1, 3. Oh, you don't have this. Let's look at that. Let's look again. So you have, the problem here is that the normal is not shown. And the normal is what matters, this one and this one. So here, clearly, you're getting closer to the normal, so 2 has to be larger than 1. If 3 is the same as 1, this is going to go parallel to the dashed line. But it goes, so 3 should be refracting more. Oh, but what matters is the difference between the index of refraction of this and this. So this is large index of refraction, but this is smaller. But if it is too small, yeah, if it is the same as when it's going to come this way, it doesn't go that way, right? It doesn't go that way. So 3 should be smaller index of refraction than 1. And it doesn't have that option. Let's see what is their explanation. Oh, none of the above, okay. Okay, so let's end it here. Again, please work on the homework assignment, finish it. And on Wednesday, we're going to start chapter 27, which is not going to be on the midterm. It is interference and diffraction of light, important chapter. Okay, see you on Wednesday.